So I started doing this video, I didn't like what I said, so I'll start again. So for each of the problems between 17 and 32, we're given the function that we're going to manipulate or transform, and that function is 2 to the x as opposed to e to the x. It's just a generic exponential function. And each of the questions has two parts. Find the indicated function, describe the transformation. I don't have to say the domain, I don't have to say the range, I don't have to sketch a graph. For part A, to find g of x plus 3, because the x plus 3 is inside the parentheses, that x plus 3 goes in an exponent, and the exponent works as a parenthesis, so I don't really need to put a parenthesis there, but it wouldn't be wrong if I put the x plus 3 in a parenthesis. And then in terms of shifting, this graph is going to go left. So for part B, it's going to go left 3. And that's all I need. Yeah, I guess I could do that. For 20, g of x minus 4, for part A of 20, find the requested function. Since the seed function is 2 to the x, g of x minus 4 is just going to be 2 to the x minus 4 power. And inside parentheses in the function notation, you move to the right. Minuses do anyways. So to describe, this is going to be the same graph as the graph of 2 to the x. It's just going to be shifted to the right 4 units. 22 wants me to do g of x plus 3 for part A, because the plus 3 isn't in a parentheses. The plus 3 doesn't go in an exponent. It just goes after the function. And pluses after the function move the graph up. So for part B, this graph is going to be moved up 3 units. Seems like a waste of paper here. 24 for part A, to do g of x minus 5. Again, because the minus 5 isn't in a parentheses, it goes after the function and not in the exponent. And then for part B, minuses after the function move the graph down. We'll do both of these. For 25a, the negative g of x, because the negative is not in a parentheses, it's going to precede the function. I'm going to get negative 2 to the x. And negatives in front of the function reflects it over the x-axis. The next one I'm going to do has a negative inside a parentheses. It's going to reflect it about the y-axis. This one, the negative's in front, so it's going to reflect it over the x-axis. And the negative didn't go in the exponent. In my 26a, because the negative is inside the parentheses, the negative goes in the exponent, becomes part of the exponent. Anytime the parentheses is something other than just x, that what's in the parentheses belongs as part of the exponent. And putting a negative inside a parentheses flips the graph over the y-axis. That's the last graph I did on the part 1 of these videos. So yeah, these are friendly. 28a wants me to do a double, a left shift and a downshift. So to create this function, g of x plus 2 minus 3, the x plus 2 needs to go in the exponent because it's inside the parentheses. The minus 3 goes after the function because it's not in the parentheses. This part moves it left 2. That part moves it down 3. A to do g of x minus 3 plus 1. when the g function is 2 to the x. The x minus 3 is going to go inside the parentheses, become part of the exponent because it's inside the parentheses. The plus 1 goes after my function. And for part b, the minus inside the parentheses, or the minus in the exponent, is going to move the graph right. And then the plus afterwards is going to move the graph up. Well, that's a horrible problem. So, oh my gosh. So 32a, I don't know what I was thinking when I wrote this. Negative g of negative x plus 1. First negative is going to stay in front of the 2 because it's not in the parentheses. The second negative is going to go inside, become part of the exponent because it's in the parentheses, and the plus 1 is going to go afterwards. The negative in front of the function for part b reflects over the x-axis. The negative in the exponent reflects over the y-axis. And the plus after the function lifts the graph up 1. Now we'll get to a new kind of problem that kind of got buried at the end of this section, but they're important problems. I know I teach these in both the lower classes, my intermediate algebra, my college algebra prep. So hopefully you know how to do these, and hopefully you do prime factoring well. So for problem 34, I know what the answer is just by looking at it, but you're not supposed to know that. So I'm going to find the answer by rewriting both sides with the same base. Any number that's not prime that's a base, I'm going to do a prime factoring for. So I'm going to do a prime factoring for 16. I'm going to say 16 is 2 times 8. 2 is prime, so I'll circle it. 8 is 2 times 4. 2 is prime, so I'll circle it. And then 4 is 2 times 2. The prime factoring for 16 is 2 times 2 times 2 times 2, which is 2 to the 4th power. What I'm going to do is rewrite in this group of problems both sides with the same base. If you can get both sides written with the same base, then you can drop the bases and set the exponents equal to each other to solve for x. So I'm dropping the 2's, and now I'm going to subtract 5 from both sides and get x equal to negative 1. That's the answer. I can check. I don't have to check, but to check, I should be able to take the number that I think is the right answer, plug it in for x, and an answer is only correct if you get a true statement when you plug it in. So if I plug in 2 for x and hit enter on my calculator, I've proved that my answer is correct, because when I put the answer that I think is correct in for x, the right and the left side simplify to be the same. My cheap calculator that I use in my lower classes is so nice for this. If you had me for a lower class, if you have this calculator and it's in mode 1, it does prime factor trees. I need to do a prime factor tree. Oh, I can't do a prime factor tree for 216. Oh, this is too advanced. What to say. I can solve this with logarithms. That's not such a good idea. Let's skip on 36 and go to do 35. And when we get to the next section, if I think about it, I'll show you how to do this an alternate way. This is a little too advanced right now. I'd have to make this 6 cubed, but 6 is a composite number. It's a little bit hard for me to explain. So let me punt on it and show you how to do problem 35, which is more fair. I'm going to do a prime factor tree for both 4 and 64. On this calculator, if it's in mode 1, if you had me for this class or another class, you would type 64, hit equals, hit the shift key, and hit the degree, minute, second quote key. Gives me 64 is 2 to the 6th power. Similarly, if I want to do a prime factor for 4, if I'm in mode 1 on this calculator, so if you had this calculator because you had me for another lower class, you type 4 and hit equals, shift and quotes, and you get 2 squared for 4. Since I don't have that, I'm going to do my prime factoring for 4 manually. 4 is 2 times 2. And then for 64, I'm going to do 64 is 8 times 8 for my prime factoring. 8 is 4 times 2. 8 is 4 times 2. 2's our prime. I just separated my 4's so that my tree would be easier to follow. Every time a number is prime, I circle it. So in my prime factoring for 64, there's 6 2's. So 64 is 2 to the 6th power. 4 is 2 to the 2nd power. Trick coming on here. If the number that you're doing a prime factoring for already has an exponent, the 4 already had an exponent and I'm doing a prime factoring for it, when I do the prime factoring, I put the prime factoring in a parentheses, and then I multiply the exponent of the prime factoring by the exponent that that number already had to clear the parentheses. So to get 35 going, I did prime factorings for both. You might have been able to get the answer in your head doing something else, but this is a strategy that you don't have to be clever for. There are other ways to do this problem, and if you've stumbled across another way, more power to you. I prefer that, but this is the way that we don't have to be smart or as clever. Once I can get both sides written with the same base, I can set the exponents equal to each other, drop the bases, and then just do the algebra to solve. I claim the answer to 35 is going to be x equal to -3. I don't have to, but I can check. If I wanted to check, the initial problem said 4 to the negative x equals 64. I'd have to go 4 to the negative from the problem, and then -3 from my answer equals 64. That I could probably enter on my calculator, or I could make the double negative positive. But if I just did 4 to the negative, using the negative in the bottom row of my calculator, bad view this morning, 4 to the -3 power, it gives me 64. So this actually does check just fine. All of these answers, if I don't make a math error, will check just fine. Awful things happen for fractions. I usually make fractions into negative exponents. For problem 38, let me get a prime factoring for the 27 underway first, and then make the fractions into negative exponents. So the 1 in the numerator, the fraction, I don't need to worry about. I'm going to make 27 into a prime factored version of 27. And I see that 27 is 3 cubed. So this problem, I'm going to emphasize, this is 1 over 3 to the first to the x minus 4 power equals 1 over 3 cubed. Now I'm going to make the fractions have negative exponents. There's a rule that says 1 over a to the n power is a to the negative n power. We actually usually say a to the negative n equals 1 over a to the n, but I need to think about that rule like this. I'm going to make each of these into a negative exponent using this rule. 1 over 3 to the first power is 3 to the -1 power. 1 over 3 to the third power is 3 to the -3 power. Now I have the bases the same. I have parentheses on the left-hand side that I need to get rid of. I'm going to get rid of the parentheses by multiplying -1 times x to get -1x, and -1 times -4 to get +4. And now I have the bases the same, so I can set the exponents equal to each other. Drop the bases of 3 and go -1x plus 4 equals -3, and then do my math, subtract 4 from both sides, and get -1x equals -7, and divide by -1, divide by -1. I claim the answer to 38 is x equal to positive 7. And I should check. So it should be the case that 1/3 to the 7 minus 4 power equals 1 over 27. Let me bring out my clunker calculator because it's just showing up better this morning. It's harder to check on this. But on this calculator, I'd go 1 divided by 3 in a parentheses, up arrow, parentheses, 7 minus 4. So I need both the base and the exponent in parentheses. When I hit enter or equals, it's going to give me a decimal. And if I hit my math button, followed by enter twice, it turns that decimal into a fraction. And it turned it into 1 over 27, which is perfect because this tells me that the left side simplifies to equal the right side, so I know my answer is correct. For 40, the left-hand side, I need to think of it as 1 over 2 to the first power, so I can make it have a negative exponent. I can make the left-hand side 2 to the negative 1 to the 3x minus 4 power. The right-hand side, 32. 32 is 2 times 16. 16 is 2 times 8. There's lots of ways to do these prime factor trees. 8 is 2 times 4, and 4 is 2 times 2. There's 1, 2, 3, 4, 5 2's in the prime factoring for 32. So 32 is 2 to the 5th. I'm going to clear the parentheses on the left-hand side. I'm going to go negative 1 times 3x and get negative 3x. I'm going to do negative 1 times negative 4 and get positive 4. Maybe I'm going to get a fraction answer here, and I'll check it. So now that I have the bases the same, I drop the bases and set the exponents equal to each other. That gives me negative 3x plus 4 equals to 5. Minus 4 minus 4. That gives me minus 3x equals to positive 1. Divide by minus 3, divide by minus 3. That gives me x equals 1 over minus 3. Looks odd to see that negative in the denominator, so I'm going to move it up front and get an answer of negative 1/3. For checking, it has to be the case that 1/2 to the 3 times negative 1/3 minus 4 power equals 32. It's going to take some heavy lifting on my calculator to get this in. Let me multiply 3 times negative 1/3 so I don't have to do too much work on my calculator. 3 times negative 1/3 is negative 1. So this is really just going 1/2 to the negative 1 minus 4. I need to make sure that equals 32. That I can check. I could even simplify that more. So 1/2 in a parentheses, up arrow, negative 1 minus 4. My answer is only correct if when I hit equals I get 32, which I do just fine. So I can check all of these. For 42, 2 is prime. I don't need to do anything to the left-hand side. 8 is not prime. I'll do a prime factor tree for it. 8 is 2 times 4. 4 is 2 times 2. So 8 is 2 cubed. Because the 8 already has an exponent, when I do the prime factoring for an 8, I need to create a parentheses and put that prime factoring in a parentheses with the exponent that the 8 had outside the parentheses. I emphasized that that x had an implied 1. I don't know that I really needed to, but I emphasized it. And now I'm going to clear the parentheses by multiplying the exponent and do 3 times 1x and 3 times minus 2. This is going to give me 2 to the 3x minus 6 power. Now that I have the bases the same, I can drop the bases and set the exponents equal to each other. And for me, it's probably smarter to subtract 2x from both sides and get 1 equals x minus 6 and then add 6 to both sides. That will give me 7 equals to x. That's supposed to be the answer. If I wanted to check this, it would have to be the case that 2 to the 2 times 7 plus 1 would equal 8 to the 7 minus 2. To check here, I need to do each side separately. So the left side is 2 to the exponent parentheses 2 times 7 plus 1. The left side comes out to 32,768. The right side, 8 to the 7 minus 2 power. The exponent has to go in a parentheses on this calculator. My newer calculator doesn't show up so well, but it does the exponents a lot nicer. I don't need the parentheses with it. Just a few more problems. For 44, the left-hand side, 7 is prime. I don't need to do a prime factor tree. On the right-hand side, 49 isn't prime. I need to do a prime factor tree, and 49 is 7 times 7. Because the 49 already had an exponent, the prime factoring for 49 needs to go in a parentheses. I'm going to clear the parentheses by multiplying 2 times x and 2 times 1. So now that I have both sides written with the same base, I can drop the bases and set the exponents equal to each other. I don't like negative x's when I'm solving, so I'm going to solve by getting the x's on the right-hand side, oh my lord, and the numbers on the left-hand side, and then I'm going to divide. I better check this one. I don't usually make fraction answers, but they can happen. Sometimes on a test, you get a fraction answer because I made a mistake. I tried to put in a problem that didn't have a fraction answer, but I came across one that did. Let me check this to see if 7 to the 4 minus 5 times 2/7 power equals 49 times the 2 to the 2/7 plus 1 power. I needed to pull this calculator out. I didn't want to do this on my other calculator, even though it's not that seeable. Just don't know what the issue is here. There's just no place to put it, I guess. Anyways, so 7 exponent 4 minus 5 parentheses math fraction 2/7. Close out my parentheses. That's the left side. Comes out to, I'm just going to round it to 2 decimals, 148.97. And then 49 exponent fraction 49 exponent fraction 2/7 plus 1, 148.97. It's good. This checks. Let me show you on my clunkier older calculator how bad this would be. To do this on my calculator, I'd go 7 exponent parentheses 4 minus 5 parentheses 2 divided by 7. Close the parentheses for the fraction, close the parentheses for the exponent. There's my 148.97. And the other side, 49 exponent parentheses 2 divided by 7 plus 1. That should work for that side. So they equal to each other. On 46, the bases are already the same. I don't need to do any prime factoring. I couldn't do a prime factoring for the e. On 46, I'm just going to take the exponent of x minus 5, set it equal to the exponent of 2x minus 4. The exponent of x minus 5 has an implied 1 in front of the x. I'm going to subtract 1x from both sides and get negative 5 equals x minus 4. Add 4 to both sides and get 9 equal to x. Let me show you that that works. That e to the 9 minus 5 equals e to the 2 times 9 minus, whoa, something's going wrong here. 2x minus 4, x minus 5. Oh, I blew a sign here. This 5 should be minus. and this should be minus 1. Let me show you that it works if I actually do it right. So e to the negative 1 minus 5 equals e to the 2 times minus 1 minus 4. Awful to do this because it's an ugly decimal. So the first side, second in ln for an e with an exponent, negative 1 minus 5. The negative, I use the bottom of the calculator to see how it's smaller. The minus I use by the plus sign. Left side is that. Right side, second in ln. So second in ln. And then 2 parentheses, negative in the bottom row of the calculator, 1 minus 4. And the right side matches. So I know my answer is okay. I don't need to write the numbers down. They match each other. 2 more problems. And it's a trick that comes up all the time in these kinds of problems. Here, all the bases are the same. On the left-hand side, I'm multiplying terms that have the same base. And there's a rule that we need to remember that says if you're multiplying terms with the same base, you can do that multiplication by adding the exponents but not changing the bases. So on the left-hand side, I'm going to rewrite the left-hand side so it only has a single e using the rule that says if I'm multiplying terms with the same base, I add their exponents. This exponent's an implied 1x minus 4. This exponent's a 3x. So the exponent can be added, and when I add them, I get 4x minus 4. Now that I have the bases the same, I can drop the e's, set the exponents equal to each other. I'm going to add 4 to both sides and get 4x equals to 6. Divide by 4, divide by 4. I think the answer is going to be x equal to 3/2. Ugh. To check this, the original problem before I did any algebra was e to the x times e to the 3x equals e squared. Here I need to go e, and I'm going to do a decimal version of 3/2. E to the 1.5 minus 4 times e to the 3 times 1.5. Make sure that equals e squared. The decimal is going to be easier on this calculator that's showing up better. And 3/2 is 1.5. So second ln e to the 1.5 minus 4, close out my parentheses, times second and ln e to the 3 times 1.5, close out my parentheses. This side comes out to 7.39 approximately. The other side, second and ln, and then just e squared. And it's the same 7.39. Because the sides equal, I know my answer is correct. Last problem with the same style of problem. The bases are the same. I'm going to use the same rule on the left-hand side to get the left-hand side to only have one of the bases. And what I do is I add the exponents and keep the base the same, using the rule that if you are multiplying and the bases are the same, you add the exponents but you don't change the bases. So now the left-hand side, its exponent, if I simplify it, it's going to be 1x plus 2. Now that I have the bases the same, I drop the bases and set the exponents equal to each other. And I get 1x equal to 3. So I claim the answer is x equal to 3, which means if I go to this problem and make this 3 to the 3 minus 2 times 3 to the 4th, that should equal 3 to the 5th. This is really just 3 to the 1st times 3 to the 4th equals 3 to the 5th. Let me do that on my calculator. So 3 exponent 1, 3 exponent, I don't know if this is going to work, times 3 exponent 4. It worked fine. Left side comes out to 243. Right side, 3 exponent 5 is also 243. Left side equals the right side, so I know my answer is good. Took 30 minutes to do it. Checked everything. That's a great idea. Checking when you can is really, really good. if you had me for another class, the calculator activities that we're going to get from the rest of the chapter, this calculator is the best calculator, second best calculator, third best calculator. All the calculators that I own will do the calculator button pressing that we're going to need for the next couple sections. This is far and away the least amount of work, the easiest, and they get progressively more complicated to work. All right, let's stop.